We are going to start with the equations of motion for uniform acceleration. We are going to start with equations of motion. Whenever we are discussing the uniform acceleration motion, let us suppose a body starts with initial velocity u, accelerates uniformly, and let the rate of acceleration is represented by a. The time for which the body accelerates is suppose t seconds, and in this course it covers a distance s meters, reaching to the final velocity after t seconds equals to v. As we know that acceleration is defined as change in velocity upon time. The rate of change of velocity is known as acceleration. Change in velocity means it is the final velocity minus initial velocity upon time taken. Cross multiplying, we will be having v minus u is equals to a into t, or we can write v equals to u plus a. This is the first equation for motion of a uniformly accelerated body. To derive the second equation, it is the distance traveled. We know that the distance traveled by the body in uniform acceleration s is equals to the average velocity multiplied with time. Average velocity, we know it is initial plus final by 2 multiplied with the time taken. Or we can cross multiply to write 2s is equals to u plus v into t. In place of v, we can put the first equation back to write this equation as u plus at multiplied with t. Or it will be 2 times of u into t plus a into t square. Divide both the sides by 2. We will be having the second equation s is equals to ut plus half at square. The second equation of motion for uniformly accelerated body. A simple equation to derive. We know distance is average speed into time taken. Average should be the sum of initial plus final by 2. Time taken to accelerate is t seconds. Cross multiply to write 2s is equals to u plus v into t. In place of v, we substitute back the first equation as u plus at and then cross multiply, and finally the value of s is being calculated. To derive the third equation using simple mathematical method, we know that v minus u, first equation gives us is equals to at, as well as the distance traveled is always average velocity multiplied with time taken. From this equation, if I write u plus v, it will be 2s upon t. This is the second equation. Multiplying equation 1 and 2, we will be having the left hand side of the equation as v minus u multiplied with v plus u, and the right hand side will be a into t multiplied with 2s upon t. T cancels with t, left hand side will become v square minus u square is equals to twice a into s. This is the third equation of uniformly accelerated motion. So first equation is v is equals to u plus at. Second equation is s is ut plus half at square, and the third equation is v square minus u square is y there. This is the derivation, which is very easy based on the mathematical concept. Now for the same information, same equations we can derive using the graphical method also. The derivations of all the three equations can be done onto the graph also. Now, if we plot the velocity time graph of this motion, time is to be taken on x-axis while the velocity is taken to be on y-axis. Body starts at point A with the initial velocity u, accelerates uniformly to reach the point B, where the final velocity becomes v, in a time interval of 2 seconds. Now see, a simple construction we are doing. Drop the perpendicular onto this axis. This point is D and this is the origin. This is the general graph of uniformly accelerated body from initial velocity u to the final velocity v. And we know that in the graph, acceleration is always defined as the slope of velocity time graph. The slope of velocity versus time graph gives us the acceleration. Slope always means it is tan theta, and in this right angle triangle, if we write the value of tan theta, it is perpendicular upon base, that is BC upon AB. BC can be represented as BD minus of CT and AC can be represented as OD. Now acceleration comes out to be V minus U upon T, gives us the first equation, V minus U is equals to A. So first equation includes initial, final velocity, acceleration and time plotted onto the graph, and slope of the velocity time graph gives us the acceleration, that gives us the first equation of motion. To find the second equation from the same graph, we know that second equation is distance. The distance covered is always the area on velocity time graph, area shaded on velocity versus time graph. Now the area will be the area of this right angle triangle plus the area of rectangle. This is the area of rectangle plus area of a right angle triangle. Rectangle area we can write with OD multiplied with OA, and the area of triangle is 1 by 2 base into height. Base is AC and height is BC. O to A, this is equals to U. So first term will be U into T plus 1 by 2 A to C. C, A to C, this is time, and B to C is V minus U. From first equation I can replace V minus U is equals to AT, so that the second equation will be UT plus half of AT square. Acceleration is the slope of velocity time graph, while the distance covered is the total area onto the shaded part of the velocity time graph. To find the third equation is independent of time. To find the third equation of motion, we know that distance covered can be represented equals to area of trapezium O, A, B, D and back to O, the total area. The total area will be equals to 1 by 2 sum of the two parallel sides OA plus BB multiplied with the distance between them, that is equals to AC. Now I can write the distance covered. 2 times of S, O to A is U, this is B, and I can write AC is equals to T. This can be represented as V minus U by T. Sorry, it is only V minus U into A. AC I have written as perpendicular to sides, sum of the two parallel sides, it will be OA plus BD, and the distance between them, distance is AC. So in place of AC I am writing T. T can be represented as V minus U upon A. Cross multiply, it will be 2 times of A into S is equals to V square minus U square. The third equation can be derived from the graph by taking the total area, converting the time in terms of U, V and A. The third way of deriving the equations is the calculus method. Using the calculus method we can derive all the three equations. Now we know that acceleration can be represented as dV by dt, rate of change of velocity. So that we can write dV equals to A into dt by cross multiply. Integrating both the sides of this equation, and when we integrate both the sides of this equation within the limits, the integration over dV. A is uniform acceleration, we have to integrate only this. When the time was 0, the velocity velocity was u. When the time becomes t, the velocity becomes v. The integration of dv is v with the two limits u to v, a as it is. Integration of dt is t with the two limits from 0 to t. Put the two values of the limit, upper limit minus the lower limit, a into t minus 0. This is the first equation, v minus u is equals to 80 using the integration method. To find the second equation using the calculus method, we know that velocity can be represented as rate of change of displacement, that is ds by dt. Gives us the value of ds is equals to v into dt, and from first equation we can write v is equals to u plus v into t. Integrate both the sides of this equation. The integration, that is when the time was 0, the distance was 0. When the time becomes t, the distance becomes equals to s. Left hand side integrates to give us value of s, 0 to s. First term will be u into t with the two limits from 0 to t. The integration of a, t gives us integration t square by 2 limits from 0 to t. Putting the two values of the limit, upper limit minus lower limit, u t minus 0 plus half of a t square minus 0 square. Solve it out. Finally we will be getting the third equation as s is equals to ut plus half a t square. The second equation using the integration method gives us s is ut plus half a t square. To derive the third equation, we know that acceleration is represented as, from simple idea, dv by dt. Cross multiply to write dv as a into dt. Now multiplying both the sides with v. Here it will be v into dt. Here it will be a into v into dt. And in place of v, on the right hand side we can write as ds upon dt. Rate of change of distance is the velocity, so that this dt cancels out. We are left with v into dv as a into ds. Integrate both the sides of this equation. When the distance was 0, the velocity was 0. When the distance becomes s, the velocity becomes v. Integration of v gives us v square by 2. Two limits are from u to v. Distance ds integrates to give us s, and putting the limits we will be getting the third equation, v square minus v square is equals to twice of a into s. So this is the three different ways of deriving the equations: simple mathematical method, the graphical method, and